Okay, so new definition. Let f be a function from A into B, and let that function be a bijection. Then the inverse function of the function f is the function f inverse, which is a function from B into A, given by f inverse is the set of ordered pairs B, A in the Cartesian product B cross A, such that the ordered pair AB is in the function f. That is, f inverse of B is the element A if and only if f of A is the element B. So notice that by definition, a function must be a bijection in order to have an inverse function. So new definition, the function which we denote I sub A, mapping the set A into itself, defined by I sub A of the element A is the element A, is called the identity function on the set A. So we will show that the identity function is a bijection. So first we'll note that the identity function is injective, since if a sub 1 is not equal to a sub 2, then the identity function evaluated at a sub 1 is not equal to the identity function evaluated at a sub 2. And we'll note that the identity function is surjective, since for every element A in the codomain A, there exists the same element A in the domain A, such that A is the identity function evaluated at A. And so, since the identity function is both injective and surjective, it is a bijection. So next, we'll prove a theorem. Let f be a function from A into B, and let that function be a bijection. Then, the composition f inverse of f is the identity function on A, and the composition f of f inverse is the identity function on the set B. So proof. First, let A be an element in the set A. Then, f inverse of f of the element A is f inverse of f of A, which by the correspondence f inverse of B is equal to A if and only if f of A is B, we have that f inverse of f of A is f inverse of the element B, which is the element A. That is f inverse composed with f is the identity function on the set A. So now let B be an element in the set B. Then the composition f of f inverse of B is f of the inverse f inverse of B, which is f of A, which is the element B. And so f of f inverse is the identity function on the set B. So as a corollary to that theorem, we will prove that if f is a function from A to B and that function is a bijection, then the inverse function from B into A is a bijection. So proof. Suppose that f inverse of B sub 1 is equal to f inverse of B sub 2. Then the composition f of f inverse of B sub 1 is equal to the composition f of f inverse B sub 2. But the composition f of f inverse is the identity on B. And so we have that the identity function on B evaluated at B sub 1 is equal to the identity function on B evaluated at B sub 2. And so B sub 1 is equal to B sub 2. And hence the inverse function is injective. So now let A be an element in the set A. Then A is equal to the identity function on A evaluated at A. But the identity function on A is the same as the composition of F inverse with F at A, which is F inverse of F of A, which is F inverse of B. That is, for every element A in the codomain A, there exists an element B in the domain B such that A is equal to the F inverse of B. And hence, the inverse function of F is surjective. So as the function F inverse is both injective and surjective, the inverse function of F is a bijection. So as an exercise, let F, which is a function from A into B, and G, which is a function from B into C, Let both these functions be bijections. Then prove that the inverse of the composition of G with F is the composition F inverse of G inverse. So now we will begin to consider subsets of the real numbers. Ultimately, our goal is to construct or develop more and more complicated subsets of the real numbers so that we can understand the underlying algebraic and topological properties of the real numbers. But we'll start with the natural numbers, and we will construct the natural numbers using the Peano axioms. So the first of the Peano axioms states that the number 1 is a natural number. The second of the Peano axiom states that if a number n is a natural number, then its successor n plus 1 must be a natural number. The third Peano axiom states that the number 1 is not the successor of any natural number. The fourth Peano axiom states that if m and n have the same successor, then m and n are the same natural number. And the fifth Peano axiom states that if A is a subset of the natural numbers such that 1 is in the subset A and the natural number n plus 1 is in the subset A whenever the element n is in the set of natural numbers, then the subset A is the entire set of natural numbers. So notice that axioms 1 and 3 together state or tell us that 1 is the least element in the set of natural numbers. And so the natural numbers begins, if we give it in order, with the number 1. So by axiom 2, since 1 is a natural number, its successor, 1 plus 1, which is 2, is also a natural number. And we can apply axiom 2 ad infinitum so that the set of natural numbers is the set of numbers 1, 2, 3, and so on, increasing by increments of 1 for infinity. So now let's discuss what axioms 4 and 5 have to say. So axiom number 4 tells us that the successor function which is S defined by S of n is equal to n plus 1. This function is injective. And then we're left with axiom number 5. And axiom 5 is the basis for the principle of mathematical induction. That is, axiom 5 is used to prove the principle of mathematical induction. And so axiom 5 is known as the induction axiom. So let's prove the principle of mathematical induction. And the statement of that principle is, let P of n be a statement that is either true or false for every natural number n. Then the statement P of n is true for every natural number n, provided that the following two conditions are satisfied. 1, P of 1 is true, and 2, P of k plus 1 is true whenever P of k is true. So proof, let A be the set of all natural numbers such that the statement P of n is true. We want to show that A is the entire set of natural numbers. So first, by the condition 1, P of 1 is true, and so 1 is an element in the set A. So now suppose that the element k is in the set A. Then that means that P of k is true. And so by the second condition, since P of k is true, P of k plus 1 is true. And so we have that k plus 1 is an element in the set A whenever k is an element in the set A. And therefore, by axiom number 5 of the Peano axioms, we have that the set A is the entire set of natural numbers. That is, The statement P of n is true for every natural number n. Okay, so we'll end here for now. Next time, we'll continue to develop more complex subsets of the real numbers. So I hope you have enjoyed the 5th lecture